Now we look at the implementation of union find in the context of SMT Solver. In the classic design, when we do get class, we need to traverse to the root. Let's suppose I want to know a class of this term T. We try to find which class it lives. We need to traverse to the root to find that particular class, which is not a constant time operation. To make it constant time, what we can add another field in each node that points to the root. That gets rid of traversing to the root. However, that creates another problem, the cost of merge. When you merge two trees, you need to update the root field each time you do the merge. That adds the cost of merging. And furthermore, in this process of updation, you need to actually traverse the whole subtree, and the subtree will require another stack such that you can go and update every point. Okay, so therefore let's use a simpler data structure, and people have realized that this tree does not give us too much advantage. Let's go for something far more simpler. We may implement equivalence classes using circular linked list, and each node has a field to indicate the root, and therefore get class is a constant time. Merging two circular linked list via next field. For example, you have a circular linked list, okay, in which s.next is pointing to the T, right? And now you have another circular linked list. This also represents a equivalence class. A node must be your root. So let's suppose in this case S is your root and V is your root, and you want to merge these classes. What do? They change their pointer to the other guy's pointed thing. So V start now pointing at T and S starting at point U, and remove these lines. And now again you got a circular linked list. Just by swapping the pointers you can easily merge, and now you have to go and walk around the smaller one and update the root field. Let's suppose you want to unmerge the circular linked list back to the original circular linked list. You need to again apply same operation again to get the merge. However, since you have probably have chosen one of them as your root, you must have forgotten which one was the loser root, and we will soon see how to keep the record of the loser root. So what happens is that for each node you will have this next pointer which records the circular linked list, and if you have a root pointer which everybody will be pointing to this representative node, and the size, because you need to update the root pointer for on the nodes whichever subsequent equivalence class has lost. And typically what you do, the loser is the smaller one, and such that you have to do less work to update the root pointer. Yeah? So you need to keep the record of the size. So how merge happens? In the merge, two circular linked lists are merged. The root fields in the smaller of the two are set to the root of the other. The smaller is computed by looking at the size field in the root node of that particular circular linked list. Then once we merge, we need to update the size in the new root by summing the size of the loser root and the winner root, and you get the size of the full linked list. So since in SMT Solver we not only merge things, we may have to unmerge it during the backtracking. We need to record such that we can backtrack. So how do we do that? This loser root in each merge, we keep them in a stack. Once we get unmerge request, what we do, we look backwards this loser roots and go back and update our classes. How the update works: let node X be the current top loser root. As soon as you start merging, you must have created a stack of loser roots. So let's suppose the X is sitting on top of this loser root, and then you ask yourself question, X is where? X must be in some circular linked list setting somewhere, right? X is here. then you ask the question, who is the root of that particular linked list? So you could do the get class and then you get this root, right? So X was the loser one, R was the winner one, and they must have swapped their pointers. Now what you do is swap again. Once you swap again, now the split which was together, R and X, you get split and you split into two simpler linked lists. And now X is the root of the part that contains X, and R remains the root where R is present. Now you need to update the size also, right? So R has a size field, X is a size field. So at the time of merge, you remember that we update the size of R, right? Not in the size of X. So X still has its old value and the correct value, so we don't need to update it. R must have a larger value. What you do? Pick the size of X and subtract with the size whatever written in the R, and you get a new size for the equivalence class where R lives.